Hello, my name is Christian Steinmetz, and I'm a PhD student at Queen Mary University of London, working with Josh Rice. Today I want to talk to you about our work, Pyloudnorm, a simple yet flexible loudness meter in Python. So the main goal of Pyloudnorm is to provide an easy-to-install package, which you can install with just one line using pip, and then you can measure the loudness of an audio file in just a few lines of code, as we show here. In this talk, we want to first discuss loudness and why we may want to measure it. Then we'll introduce the ITUR BS1770 recommendation and give a brief overview of the algorithm. Following that, we'll discuss a number of modifications that have been proposed in the literature thus far that aim to improve the performance of these measurements. Then with that, we will introduce Pyloudnorm and the design of the library, as well as outline some of its features. To conclude, we will then discuss an evaluation we performed, looking at Pyloudnorm and if it's compliant, as well as investigating a number of other loudness implementations that exist. So first, to discuss what is loudness, this comes from the reality that humans perceive sound pressure on a nonlinear scale with respect to both frequency and intensity, which means that if we want to measure the loudness or compare the relative loudness of two stimuli, this can be challenging because we cannot simply just measure the energy of these two signals and compare them. This phenomena has been well studied in psychoacoustics and auditory perception and has a long history, with a number of different models based upon listening tests and psychoacoustic analysis being proposed in the literature. The problem is that many of these psychoacoustically informed models are often too complex and don't fit the use cases we have in audio engineering, for example. There has also been a lot of interest in, loudness for music specifically to normalize playback levels. To kind of formalize all of these and propose a standardized method for measuring loudness that's both simple and easy to use, the ITUR BS1770 recommendation was introduced, which attempted to do just that and has now seen widespread adoption, most notably in the EBUR 128 recommendation that dictates loudness levels for broadcast. So the ITUR BS1770 recommendation includes a description of the measurement of integrated loudness, which is what we focus on in Pyloudnorm. And basically the main motivation for this algorithm is to provide a simple way to measure loudness of electronically reproduced signals, that being digitally recorded signals, or in the case of live broadcasts, for example, so that we can compare these relative loudness of the signals. So here I just want to walk through briefly on this diagram the different steps of the process, but this is just going to be a very high-level overview of the algorithm. So to begin with, we take the individual channels of the recording that we want to measure and apply what they call this K-filtering. And this is simply a two-stage filtering process, where in the first part we apply this high shell filter, as you can see in this figure reproduced from the original recommendation. We boost the high frequencies above 1 kilohertz. And this is then followed by a high-pass filter that removes the influence of low frequencies to more closely match the response of human sensitivity. Once we have filtered the signal, we then split the filtered signal into blocks that are overlapping of 400 milliseconds. So these blocks are then passed on so that we can then compute the energy of the signal within each block. Then we apply individual channel weighting based on which channel is being used. In this diagram, I'm showing just a simple stereo case, but in the case of a multi-channel format, there are individual weightings to be applied to the different surround channels, for example. Then once we have applied this channel weighting, we can then apply this log scaling to the energy in each block, and then we apply this specialized gating, which allows us to remove blocks below both this set absolute and relative thresholds. And this gating mechanism is one of the key parts of the algorithm. To apply this gating, essentially the final loudness measurement looks as it's shown in this equation here, where we simply disregard the energy of the blocks that are below this threshold. For more details on how these thresholds are computed, please refer to the original recommendation for more details on that. But this just is meant to give a high-level overview of how the algorithm is operating. So as I mentioned before, the main motivation for the ITU BS1770 recommendation was for use in broadcast, essentially. But due to its simplicity, there's now been many use cases for this algorithm outside of broadcast. For example, automatically normalizing stimuli for listening tests is a common use case, especially when these are distributed online. Also, automatic loudness-based multitrack mixing, where systems have been designed that attempt to make a mixture of individual tracks based on loudness measurements. There's also recently been an increasing use case for these kinds of loudness measurements for pre-processing audio data sets in machine learning use cases, and also using loudness features in machine learning itself, both as a feature and for data augmentation techniques. In the standard, though, they make it very clear that the algorithm that it's been designed here really only correlates well with human perception when the signal in question is broadband in nature. So in the case of narrowband signals, for example, individual instruments, it's clear that the loudness recommendation may not produce measurements that agree with perception. And since there has been a growing number of applications, as I showed on the previous slide, that maybe consider content that's more narrowband in nature, these modifications are becoming more relevant. So to outline some of the modifications, some of the first came from this paper from Cabrera et al. In 2008, and they proposed a new set of modifications based on further listening tests, where they adjusted the cutoff frequency of the high-pass filter to 149 hertz, and they replaced the high-shell filter with a notch filter centered at 1 kilohertz, which they found produced measurements that correlated better with perception. Pestana et al. Also looked at these similar questions specifically within the context of applying this loudness algorithm for multi-track mixing. And they recommend using a smaller gating block size and adjusting the overall gain of this high shell filter, which produced better results for measuring the loudness of the individual stimuli to create better mixes. Fenton and Lee in 2017 made another modification for considering automatic mixing cases, and they proposed boosting the gain of the high shell filter by 5 dB and changing the cutoff of the high pass filter to 130 hertz, which is similar to the recommendation from Cabrera et al. And they also proposed the addition of this peaking filter with a center frequency of 500 hertz. So basically, as you can see, a lot of these modifications are focused on adjusting those two main aspects of the algorithm, mainly the pre-emphasis filtering, as well as changing the block sizes. But even more recently, the man in 2018 stated that the algorithm produced in the original specification actually only provides filter coefficients at 48 kilohertz, and it doesn't actually define filter prototypes for other sample rates. So in this work, they reverse engineered the filter specification, which enables us to create completely compliant filters at any sample rate. So now that brings us to our discussion about Pyloudnorm. And the main goal is to have a simple to install and run, but also flexible library that enables us to implement these modifications as well as future modifications. So as I've shown before, here's just a simple few lines of code that show how we can measure the loudness using Pyloudnorm. So assuming we've imported the correct libraries. Here you can see how we've imported Pyloudnorm. We're using Soundfile, which is another Python library for loading audio. So on the first line here, we load the audio, and then the next step is to create a meter here where we create just the basic BS1770 compliant meter by passing the appropriate sample rate. And then we can measure the loudness just by calling this integrated loudness function and passing our data to that function, which will return the loudness value across that entire piece of audio in dB LUFS. So one of the key aspects is, while it's easy to create a standard meter just by passing the default values, you can also modify all of the underlying algorithm parameters that are needed to utilize those proposed modifications. And we built the library in such a way that it's easy to adapt those. So for example, while creating the meter in the default format, we'll create a meter with the standard 400 milliseconds block size. You can adjust that block size by passing that in as an optional keyword argument when creating a meter. But that covers just the block size adjustments. We also have the ability to adjust the different filters. So we have already created filter class specifications for the filters mentioned in the previous papers. And you can simply select those filters by passing in the optional string to specify which of those filters you want. And this makes it really easy to adapt those modifications if you so desire in your use case. We also enable future modifications as well as experimentation with the use of this simple IIR filter class, which has a number of different filter prototypes like high pass, high shelf, and other types of common filter designs. And using that, you can then create your own K-filtering stage with any number or design of different IIR filters. And this enables Pyloudnorm to be potentially facilitate the use of new modifications that may arise, and is also can be used as a platform for experimentation for future modifications to the algorithm as well. Now this brings us to the evaluation. And in this section, we want to ask the question first, is Pyloudnorm a compliant meter with the original BS 1770 standard? And we also ask, how does it compare to other loudness implementations of this standard? So there are a number of publicly available implementations that predate Pyloudnorm, and they come in a variety of different forms with different potential use cases. So in this case, we're considering just using them from a Python interface. So one such option is Essentia, which is actually a large library for music and audio signal analysis. And within that library, they have one function that implements the standard that you can use to do integrated loudness measurement computations. And while this is certainly a good option, it has one drawback in that it's quite a large library to install due to the fact that it has such a diverse set of options. So in cases where only loudness measurements are of interest, it may not be the best choice. FFmpeg is another popular option since it's a commonly available command line tool for editing audio and video, and they include some loudness features as well. The only problem is that it requires, making command line calls to measure loudness, but there are a number of Python wrappers that allow you to make these calls pretty easily from Python. There's also libebur128, which is a pure C implementation of the algorithm, and there's a number of other tools that use this as a base for their implementation of the algorithm as well, one of them being Loudness Scanner, which is an easy tool for measuring the loudness of audio files stored on your computer. Then, most similar to ours is this loudness.py implementation from the Demand 2018 paper that implements their proposed modifications to the filters that more accurately match the filter design in the original specification. And this is an implementation in pure Python using NumPy as Pyloudnorm does. The only main drawback of loudness.py is that it's simply provided as a simple Python script and is not built into a package that can be easily installed like Pyloudnorm can. We also consider two different commercial options, one of them being the loudness meter that's provided in Adobe Audition. And we also consider this ulean meter, which has an online portal for measuring the loudness of files that you can upload. So we compare Pyloudnorm against these 6 other implementations. To begin with in our evaluation, we consider the compliance material that's provided as part of the BS 2217 standard, which provides compliance material for the original standard. So in this case, they provide a number of different sinusoidal tones and frequency sweeps with provided target values of what a compliant meter should measure on those files. The standard states that all compliant meters should measure within plus or minus 1 dB LUFS of the specified target value. So to evaluate these meters, we simply report the measurement of all of these compliance material files as shown here in the table. What's interesting to see is that there are a few cases here marked in boldface where these meters do not meet that threshold for compliance. The first one of note is Essentia, that appears to have some discrepancies in the loudness measurement for lower frequency sinusoidal tones, which we'll talk a little bit about more in the next slide. Also, it appears that both FFmpeg and ulean provide slightly different measurements on the relative gate test, which indicates that there may be some slight difference in how their algorithm handles gating of the signal or padding of the signal at some place. And also of note, while loudness.py provides mostly compliant measurements for the other files, on the absolute gate test, there's also an indication that their meter is a few dB LUFS different from the target here. And in the code there, we think it's likely that this is due to some small difference that occurs when handling silence in the audio, and that this somewhat changes the value. So as mentioned, there was some indication that the filters in the Essentia implementation deviate somewhat from the original standard. So to test this, we simply measured the loudness of pure sinusoidal tones at very low frequencies and plotted the loudness from the different meters using those different sine waves. And as you can see, pretty much all the meters follow the same curve, with Essentia having a kind of significant difference here in the ultra low frequencies. And it's likely that there's some sort of issue that happens in the filtering or in some other part of the algorithm. As a further form of study, we also tried to create some more challenging compliance material to test how the different implementations would react. In this case, we don't have actual true target values. So what we do is simply take the mean reading across all of the different meters, and we report this in the column here. And then we have marked in boldface here any meter implementation that measured greater than plus or minus 5 dB LUFS from that mean difference, which indicates that it deviates from all of the other meters pretty significantly. So we see kind of a similar story here as we would expect in this 16 kilohertz sine tone, that Essentia performs quite a bit differently than the other meters by a fairly significant margin. We also see that, for example, in these few examples here that contain just individual instrument notes, that FFmpeg is also reporting significantly different numbers for some of these tests as compared to the mean. And again, it's not clear what's causing these differences, but it seems that it could have something to do with how the audio is loaded and how audio samples may be padded at the beginning or end that would change how the gating is functioning. Finally, we also see that the ulean meter, which provides this online interface, while it was mostly compliant in the last table with the compliance material, it seems that a lot of these different tests that we've used here have created significant discrepancies among the different meters. Basically, these results kind of give an indication that you should be careful when using different meters, especially when you're going to be comparing values between them, because these normalization values between two different meters can be of multiple dB LUFS, which is certainly an audible difference. As a final test in our evaluation, we also compare the runtime of the different algorithms. To make this fair between the implementations that use audio loaders outside of Python, we also count the time it takes to load the file using PySoundFile for the Python implementations, and this makes it a more fair comparison. And in this case, it's clear that both loudness.py and Pyloudnorm provide the fastest options when considering running this from a Python environment. That makes sense simply because it doesn't require any external calls to the command line, whereas the other first three options like FFmpeg, Essentia, and libebu R128 all require additional code to make these calls. So from a Python perspective, the pure Python implementations really are kind of the fastest options. All the code for Pyloudnorm is open source and it's fully available on GitHub, which you can check out here at the link below. Please contribute if you have any improvements to make, and we're open to taking any pull requests. Also, all of the code for our evaluations that I've discussed in this paper, along with the data from those tables, is also publicly available in this other repository called Pyloudnorm-eval. To summarize Pyloudnorm, the first most important aspect is that it's an easy to install and use loudness package. It specifically implements the ES 1770 loudness recommendation and is fully compliant as a result of our tests. In addition, it is one of the only implementations that enables modifications of the underlying algorithm parameters, and this also enables future improvements to be incorporated. Finally, it's one of the fastest Python options available as compared to the other implementations that we evaluated in this paper. That concludes our talk for today. I hope you enjoyed it, and thank you so much. If you have any questions, please feel free to reach out. I'm more than happy to discuss further any details of the paper. Thank you.